All right, my dudes, this is 21 merge two sorted lists. Okay, this problem isn't that bad, honestly. But if you do it the wrong way, the pointer manipulation gets confusing, and you kind of have to mess with the fact that I'll explain it after we get started. But merge two sorted link, first time doing this problem, by the way, actually true. So we're going to be merge two sorted linked lists. So these are the two linked lists. They're sorted 1, 2, 4, 1, 3, 4, and return it as a sorted list. They don't mean sorted list, they mean a sorted linked list, basically here. The list should be made by splicing together the nodes of the first two lists. What does this mean? This means that we can't make a new list. So this line is really just separating the outcome here, but if you imagine this, we can't start with a linked, kind of like an empty node here, and kind of go through. So we could kind of make a new, or start a new linked list node here and just kind of choose between them and kind of add the values here. We're supposed to kind of do this like, not in place, but kind of in place in air quotes. And so how can we go about doing this, right? So if we have to do this as a sequence of pointer manipulations, if you do this so the first way you can do this, well, it's going to be really confusing. I'm not even sure if you can complete it without tearing your hair out. But imagine you start this as the first node, right? You just assume that you're going to start with this as the first node. Well, you can't do that, right? Because what if the list is 0, 2, 4 and 1, 3, 4? We started at 0, and now the first node in the list actually should be 0. But okay, you start on the other list, but it could be that this list is the first one, right? So you have some confusing stuff there. So you already have logic just to choose which linked list or which node you're going to start with, right? So because if you don't create some intermediary list node, it's going to be really confusing. And so one way you can kind of imagine this, one easier way to do this, if I open this up here, what you can do, let me draw on this real quick, markdown. Okay. Oh, maybe it's this. So what you have to do, I mean, you don't have to, but it makes this much more simpler. So just going with what we said earlier, if we do start here, right? Let's just assume since 1 and 1, we'll just roll with the example, right? So you start here. Let me change my color. Yikes. So you start here, right? And now, right, you have to insert into the list because we said you can't make a new list because we want to just be a splicing together nodes of the first two lists. So you have to choose between this and this, right? So what you can do is say node.next and just choose a smaller value, right? And then you kind of erase this one here and go like this. And then you'd be here, and then you have to choose between these two, and you'd go like this. And then you choose between these two, and then you go like this. And then you have to choose, oh, you wouldn't take this out. You choose between these two, and you go like this, like this, like this. But I think you can do it this way, but the way the problem, because I think this was C++, you could do it this way. But the way that we're working with this in Python, I don't know if there's a way that you can do it that way. Oops, I shouldn't have closed that. So another easy way to do this is if we make this bigger, we can actually make another load, and basically you can probably do it the other way, but this way you're just going to simplify the pointer manipulation so much. If you start here, just kind of make up a node. What you can do is just choose between the ones that go to the next node, right? You can just kind of be an observer here. Which one's smaller? Doesn't really matter. We'll just choose this one, right? And then we'll be like, oh, which one's smaller? Because we'll always be one behind, so we can kind of just choose, and we'll increment this, and then we'll choose between these two. It'll be this one. You end up with the same result, but the pointer manipulation is going to be far simpler. So we can kind of work through that here. So like we said, we're going to create one node right before it starts. It's going to be called pre. We're just going to make it empty list node. We can just call a list node here because they said it was defined like this. And then what we're going to do is we're going to set head, which is going to be our kind of our connection to the whole thing, because we want to return, at the end we have to return something that's pointed at the head, and pre is probably going to end up all the way at the bottom, right, at the end of the list. So we just need something that's connected to the top. And so what we're going to do, right, we said that we were going to, we have to iterate through both lists, right, to check whether or not which value goes into it. So we're just going to do while L1 is not none and L2 is not none. So while both of these pointers aren't at the end of their lists, of their linked list. So L1, so 4 here has another pointer you kind of can't see, but it's a next and it's just pointing to none. So while we're not there, which means while we're not at the end, and while the other one's not at the end, we want to do this loop, right? And it says we want to return it as a sorted list. So how do we do that? We just have to choose the smallest value between these two. So we're going to say if if L1.val is less than L2.val, then what we're going to do is we're going to set prev.next, and here's kind of where the magic of staying one behind is. You can kind of just mess with this pointer without messing with the way the lists are set up, at least initially. Or I guess you don't want to be in the action, basically. Kind of like when you're deleting a node in the list, you don't want to be the node that you're deleting. You want to be before the node you're deleting. So we can do prev node.next is equal to L1. Why L1? Because L1 is smaller than L2, and we want this to be in order. Then what we're going to do is we're going to increment L1, and what that means, we're going to sequentially move it forward one node in the list, and we do that by saying L1 equals L1.next. Otherwise, then L2 must be smaller, right? So we can just say prev.next equals L2, and then we'll just move the second pointer. It's the node that we're working with in the second list to over one node. Now, to keep this consistent, we can't move through the list, right, without incrementing prev.next. Otherwise, we would just only ever have two nodes in the linked list. The first one we made was a dummy node, and the node that we just keep replacing it with, right? So you have to move prev over some. So what we can do is do prev equal prev.next. And we need to have this step for both of them, right? Whichever one goes here, we still have to move it forward once. And so that's a pretty simple solution that you can kind of run with, and you kind of end up with the answer there. The only problem, though, if we blow this up again, so let's just say we got to the end. It's going to be something like this is our dummy node, goes here, goes here, goes here, goes here, and then this, it doesn't really matter here. It's going to be whichever one, because of the same value, goes here, right? And so because our thing says and here, we're always going to end up where it's possible that one of the lists is going to have an extra set of values, right? So it's always possible that one of the lists, because of the way this loop works, one list will always have leftover values, right? And so we have to do the thing where after the list is done, I'll drag this down. Once the list is done, there has to be some effort made to finish this connection, right? And what's cool about this is even if there's another list here, another node in the list, just this last bit of housekeeping here is going to handle that, because we're just working with pointers here. And so if we just say node.next here, we get the rest of the values in the list, no matter if this kept going for forever. We just automatically get the rest of the values because they're all linked together because they're a linked list. So to do that, we're just going to say, well, prev.next is going to be equal to L1, so it's a ternary operator, if L1 is not none. Else, so if L1 is not none, so if L1 is the list that still has items in it, then just pop the rest of them on there. Else, we're just going to pop L2 on there. And so that's kind of the rest of this problem, but if we take a look at this one last time, we'll blow this up. There's one last thing. So we're working, if you boom, 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 we did the housekeeping, right? But if you notice, we did prev.next equals L1 or L2. That's going to finish it, right? But if we were to return our head, because head is going to be where we started, if we pay attention, if we return head, this is head right here. and that's clearly not part of the node linked list. I mean, the merged sorted linked list. So what we have to do is we want to return head.next, which is going to be the start of this, of going to be our sorted linked list. I mean, our sorted merged linked list. So what we can do is head.next. And I think this should work. Yeah, okay, so this is pretty good. First time doing this problem, by the way, actually true. But that is merged to sorted lists. The time complexity here, although it seems like it's linear time, it's really not. Because we're iterating through, this while loop is just one while loop, but we're iterating while both lists are not empty. And so what we're really iterating over here is of O of m plus n, where m is the length of the first list and n is the length of the second list. So that's what that's going to take. And this is going to take constant space, because this is why they specifically request that we splice together the nodes of the first list. I mean, we create this variable here, and maybe one or two other variables for housekeeping, but that's kind of irrelevant because our variables that we use for this algorithm aren't going to scale with the size of the input. So that's going to be constant. And that is 221 merged to sorted list.